My name is Alex Wezel. I'm a PhD student in the group of Professor Wolfgang Kunz at RPTU Kaiserslautern-Landau here in southwest Germany. And I'm very happy to present you the joint work of our group and our former colleague Mohammad Fadihe, who is now postdoc at Stanford University. Today I will give you a brief overview of how we aim to advance in the field of hardware security verification. And although I had already many speakers before me who did very good on motivating why we need it, I want to give a quick motivation. So since 2017, with the detection or the discovery of the infamous meltdown in Spectre attacks, hardware security got a new sparked interest. Since then, industry and academia, they found multiple various vulnerabilities, and they fill whole databases like the CVE and the CW with it. But still, we know already there are so many attacks out there, but we need to make sure that our designs don't contain any unknown ones. And unfortunately, conventional testing methods don't give us exhaustive security guarantees, and they usually don't scale that well. And that's why we need some formal methodologies that give us these security guarantees. But before I talk about our method, I want to give a brief definition or an intuition of how we see a secure system. And I want to do this with a classical Spectre attack that violates the confidentiality of data. So assume we have a system with a CPU that runs some program, and we have a memory that is can be partitioned into a public part that is regularly accessed by the program and a confidential part that is never accessed sequentially by the program. So in a Spectre attack, what happens is that the attacker mistrains the branch predictor so that some victim program accesses the confidential data transiently. This data will then be somehow encoded in a microarchitectural buffer, typically the cache, and this happens all before the misspeculation resolves. Then, after the misspeculation, an attacker program is able to extract this microarchitectural footprint, for example, with a flush and reload attack, and thereby deduce the value of the secret data. So what we can observe is that the confidentiality is violated here because the secret data is able to interfere with the execution of the attacker program. That means, on the other hand, if you want to guarantee that a system is secure with respect to confidentiality, we need to make sure that it executes uniquely with respect to this data. And with uniquely, I mean independent of this data. And to this end, we came up with unique program execution checking, or in short, UPEC, which is a formal, exhaustive methodology that detects all propagations of informations from or to signals of interest. And I have to note here, we do this on the RTL. This means we can detect violations of confidentiality, as for example, possible accesses, propagations, and leakages of confidential data. But we can also look at integrity, where we have, for example, an untrusted IP that tries to maliciously interfere with the protected state of our system. Initially, UPEC was developed for processors. That's why it's called unique program execution checking. But it works in general for any system, and it makes sure that a system executes uniquely with respect to the signals of interest, so, which we will call the source of discrepancy, or in short, the SOD. So why should we use UPEC? What is so nice about UPEC? Well, as I said, it's a formal methodology which allows us to have exhaustive detection of all vulnerabilities in our designs. And the computational model, which we'll see in a minute, helps us because it allows us that we can separate functional verification from security verification, because our methodology is independent of the functional correctness of the design under verification. The computational model also improves the scalability of our method, because we can demonstrate that we also are able to verify out-of-order cores or even whole SoCs, although it is a formal method. And what we will see later in our case studies is that we were able to adapt UPEC to different threat models, and thereby can cover many attacks. So let's dive into the technical details. We aim to only use one property that is pretty general. We don't want to have many properties that need to know about every tiny detail of our design. So we want to prove that our system executes uniquely. That means we need something to compare it against. That means we take our design under verification here in blue and we duplicate it so that we have a MITRE model, also sometimes called a two-safety model. Now, we have something to compare it against, but we need to say with respect to what it should execute uniquely. And that's why we need to define the SOD here in red, which is the source of discrepancy, or the signals that we want to observe, where can they propagate. So what we do next is we say, okay, except for this SOD, all our inputs are constrained to be equal for the whole time window. And we assume that at the beginning of our proofs, the state signals, except for the ones contained in the SOD, are also equal. The choice of the SOD depends on your threat model. So for example, for confidentiality, you could say you choose some signals in your data memory and say, okay, I want to observe, is this confidential data, is it able to propagate somewhere? And for the threat model of integrity, for example, you could say, okay, I assume I have some untrusted IP connected to my system, so I can take one of the inputs as the SOD to model that this IP can do whatever it likes to. So now that we have this model, we can create the generic UPEC property. So what does this property do? We assume that, as I said at the beginning of our proof, all states except for the SOD are equal between the two instances. Also, the inputs to both instances are the same except for the ones contained in the SOD. What we then want to prove is that all the states and the outputs remain equal for the next k clock cycles. This means if this property holds, so if we can prove this for some design, this SOD is not able to propagate to any other location or any other state signal or output in the design, which makes it secure, or at least if the propagation, if there is no propagation in the design. It may be that you need to add some threat model dependent constraints. So for example, if you verify confidentiality and you say you have some secret data in your memory, then of course our SAT solver may just find an example where you just have a user process, it tries to access the data, but the data is not protected, so it can simply do it. So maybe we need to specify that this data is protected via a PMP. The nice thing about this property is that the only difference in this MITRE model is the SOD. So all counterexamples to this property must depend on this. And because we have these two instances and we can see what is different between the instances, we can easily track what is the root cause for this propagation. So now that we have the property, let's see how we can use this property to design secure systems. So at the beginning, of course, we need to set up our MITRE model. We need to define, okay, what is our threat model? What do we choose as the SOD? And what are our threat model dependent constraints? If we have this, we can write the UPEC property and check it with any formal tool and inspect if there are some counterexamples. Then we can have two cases. In one case, we see, okay, the SOD propagates to some signal, but this propagation isn't harmful. It's not violating the security. There may just be some propagation and it will be stopped later on, then everything is fine. What we do then is we take our SOD and add the signal that was affected to it. By this, we don't consider this counterexample as a violation of security anymore, and we can check if there are more propagations. And if we at some point find a propagation that violates our security, then we need to fix this. But because of this nice model, we can easily track down how the SOD propagated up until there, and we can think of an appropriate fix. If we repeat this process until we have no more counterexamples, we can guarantee that the design under verification is secure with respect to the defined threat model. So now I talked about a lot of technical stuff, but let's look at some of our experiments. And here I want to highlight our version of UPEC for data-independent timing. UPEC DIT is able to detect data-dependent timing in accelerators or processors. For processors, this is even nicer because we can qualify individual instructions as data oblivious, which is especially important in the context of constant time programming. We analyzed multiple processors and accelerators, but here I want to give a highlight on our experiment on IBEX, because IBEX is a core that features a dedicated CSR for data-independent timing modes. So the developers thought about this while designing it. And still, we found timing dependency in IBEX, even in the data-independent timing mode, which is due to misaligned addresses for memory accesses. And I have here a small example. So let's say someone wants to load from address 2 and wants to access this 4 blue bytes. Then what IBEX will do is, IBEX will translate this access into 2 aligned accesses, because I think the memory is not able to handle the misaligned ones. And on the first glance, this looks like everything is okay, but it is not, because we have a different number of memory access dependent on the address. So if the address is aligned, we see only 1 access. If it's misaligned, we see 2 accesses, and an attacker can observe this, for example, by measuring the execution time. We reported this bug, and the developers also confirmed that and updated their documentation accordingly. I have some more experiments where I want to briefly talk about. So we also did experiments on UPEC for transit execution attacks, especially in out-of-order cores. Here, in this case, it was Boom. We found multiple spectral variants and also a meltdown vulnerability in that. And we also came up with a secure by construction design methodology for out-of-order cores, where we use UPEC to iteratively verify our incremental design. And by that, we produced the first formally verified RTL implementation of an out-of-order core that is secure with respect to transit execution attacks. But UPEC is not only applicable to cores or functional units. We can also go bigger and target SoCs. So we did experiments about functional security bugs in SoCs, and in this case, it was the Pulpissimo SoC. And here we found a confused deputy attack, as mentioned in the talk before, where we have our core instrumenting a hardware accelerator to access confidential data and circumvent the PMP and just put that data to an output port of the SoC. So far, I only talked about confidentiality threat models, but we also made it to use UPEC for integrity verification, especially operation integrity in SoCs. And we looked at the OpenTitan design, and we assumed that, okay, let's say someone just plugs in some third-party IP that you maybe can't trust, and we found a denial of service attack using this untrusted IP, where the untrusted IP didn't conform with the bus protocol and led to a deadlock for one of the master components. If you're interested in the papers or more details, please refer to our papers. Yes, so let me shortly summarize my talk. I presented UPEC, a formal methodology which is scalable and exhaustive. We presented multiple case studies that show the versatility of UPEC and that it's easy to adapt it to different threat models. And we envision that UPEC will be used as a hardware root of trust, to provide a hardware root of trust for the higher levels of the system stack. Then, last but not least, I want to thank all my collaborators. It's many people who helped us with this work. And then I want to thank you for your attention.
Thanks, Alex. I guess we got time for a question or two. Any question? Yes? Yeah? No? Oh, Wezel.
Yeah, hi. Just for clarification, because security is not my background, the scalability of the methodology comes from the fact that you look for T plus K time steps. Is it similar to, let's say, bounded model checking?
Yes, you're right.
Just for security?
you're right. So the property that I've shown is a bounded one.
Okay.
But in fact, I couldn't add it to the presentation because it would be too much details. But in fact, we also employ additional inductive proofs that verify that we have, for an unbounded time, we have no propagations.
Perfect, thanks.
You're welcome.
Any other question? Yeah, over here.
Thank you very much. Do you think you can parallelize the model checking? So in the world of parallel computing, is this a parallelizable task?
Yes, actually this is also one of the techniques that we use for our proof simplification to make it more scalable. We basically check, can we propagate our SOD to some of its fan-out? And we can split checking all of these fan-outs or all of the signals in the fan-out at once into checking it in multiple properties and parallelize them. And we can thereby use this cone of influence reduction to make the properties faster.
Okay. Any other question? Okay, so thank you, Alex.